In the last session, we saw the definitions of P and NP, and we saw how to prove NP hardness and NP completeness. And we also saw two NP complete problems. So the first one was the one that you're supposed to trust me. CNF SAT is NP complete. I will put a proof of this on Canvas. But then as soon as we had one NP complete problem, we could actually use it to find other NP complete problems. So we looked at 3SAT, for example. And in order to prove that 3SAT is NP complete, I had to prove two things. I have to prove that it's in NP, which was pretty easy to show. And then I had to also prove that it's harder than an NP hard problem. So I took CNF SAT and I reduced it to 3SAT, which proves that 3SAT is harder or at least as hard as CNF SAT, which means that 3SAT is NP complete. Okay, so the whole point of this session is to see more and more reductions and to see several other NP complete problems. Okay, so this is what we have, NP complete problems. Right now, these are the things that we have. Well, first of all, we have any problem in NP. And I know that any problem in NP can be reduced to CNF SAT. Okay, so I'm just assuming that. But let me just put the NP complete problems in this picture. So I'm going to start with CNF SAT. And towards the end of the last lecture, we saw a reduction from general CNF SAT to 3SAT, where every class has only 3 literal SATs. Okay. Of course, I also have a reduction in the opposite direction. In this case, it's very trivial because 3SAT is a special case of CNF SAT. So if you have a 3SAT input, that's also a valid CNF SAT input. So I also have this reduction, which basically shows that these two problems have the same hardness. If you have a polynomial time algorithm for one of them, you have a polynomial time algorithm for both. And of course, you will also have a polynomial time algorithm for everything in NP. And when I'm saying algorithm, I mean deterministic algorithm, a deterministic Turing machine. But today we're going to see a lot of other problems that are also NP complete. So all of these NP complete problems have the same difficulty in the sense of one of them, you have solved all of them in polynomial time. Okay, but of course, as I mentioned in the last session, we don't know if P is equal to NP or not. So for all the problems that we're going to see today, no one knows if a polynomial time algorithm actually exists. There are a lot of beliefs. It's kind of like a religion. Most computer scientists believe that P and NP are not the same. And of course, NP complete problems are the hardest problems in NP. So most computer scientists believe that you cannot find a polynomial time algorithm for any of the NP complete problems. But we don't have a proof. So it's possible that it actually exists. Okay, the first problem we want to see today is independent sets. So I want to find a reduction from 3SAT to independent sets. Let's actually define what this is. So independent sets, or IS, is a very simple problem. In the input, I'm going to give you a graph. So the input will have a graph, let's call it G, with vertex set V and edge set E. And this is an undirected graph, okay? And because I want to have a decision problem, I'm not going to ask you to give me the largest independent set. I'm just going to give you a number K, and I'm gonna ask you, is there an independent set of size K? So my input will contain a graph, and it will also contain some number K. And the output should be yes if there exists a subset of K vertices. So if there exists some subset, let's call it I, subset of V, such that it has exactly K vertices, so the size of I is K, and there are no edges between vertices in I. So, and there is no edge with both endpoints in I. Of course, as you would know from 2711 or graph theory courses, such a set I is called an independent set. Okay, so basically in the independent set problem, because I want to have a decision problem, I'm giving you a graph and I'm giving you some number k, and I'm asking, is there an independent set of size k? Again, naturally, I would normally ask for you to actually output an independent set of size k, or to give me the largest independent set and so on. But remember, I want to keep my problems as decision problems, because we have already seen that if I can categorize my decision problems, and if I can solve the decision problem in polynomial time, then I can solve the optimization variant as well. I can just do binary search. Okay, so whenever I talk about the independent set problem, this is what I mean. I mean that you're given a graph, you're given a number k. The question is, does this graph have an independent set of size k? Of course, instead of saying of size exactly k, I can say greater than or equal to k, but this doesn't change the problem at all. Because if you have an independent set with k plus 1 vertices, just kick out one vertex, and then you have an independent set with k vertices. Okay. So I want to prove that this problem is NP complete. I have to prove two things. I have to first prove that it's in NP. In order to prove that it's in NP, I can do one of two things. I can either create a non-deterministic Turing machine that solves this problem in polynomial time. We've seen an example of this for tree coloring in the previous session. Or I can use the other definition of NP, which says that when the answer is yes, you can give me a polynomial size proof, and I can verify that proof in polynomial time. Okay, so if I have an input to this problem and the answer is yes, it means that my graph has an independent set of size k. So I can just use that independent set, the list of vertices that appear in that independent set, as my proof. And my verifier would just take this proof, and of course, it would also take the original input, and it just verifies that it's really an independent set, that none of the edges go between edges in this claimed set. And of course, this verifier would run in polynomial time, so the problem is in NP. Again, this part is usually the easy part, but I'm repeating this 100 times. If you don't do this part in the exam, you will get a 0. Okay, you have to prove that the problem is in NP. Now that the problem is in NP, I want to prove that it's NP hard. And this is where I do a reduction. And I want to do my reduction from 3 sets. So basically, I want to say that my problem is at least as hard as 3 sets. And the way I do this is I assume that someone has given me a black box algorithm that can solve the independent set problem. Using that, can I create an algorithm for 3 sets? And can I do this in polynomial time? Okay, so again, we've seen the formal definition of a polynomial time reduction last time. So let's just get into this. Here's the reduction that I want. So my input to the 3 set is going to look like this. I'm going to have a bunch of clauses, and let's say I'm just going to do an example here, but generally my clauses are of this form, like X or Y or not Z, and not X or W or Z, let's say, okay? So I have a bunch of clauses, and each clause has exactly 3 literals. And I have ors between literals, I have ands between clauses. Now, if I want to write this in its general form, the way you have to write in the exam, it looks a bit bad, because if I want to have the most general case, I have to say that this is and for, let's say, I from 1 to some number n of L, or of j from 1 to 3, Lij, where every Lij is either a variable or the negation of a variable. But I mean, that's not how humans think. So instead of writing it formally like that, let's just look at this example. And let's explain how I'm going to take an input of 3 sets and convert it to an input of independent set. Now, the really important points are that I have to do this, first of all, in polynomial time. And secondly, I have to create an equivalent input. So if the answer to my 3 set is yes, the answer to my independent set input should also be yes. If it's no, that one should also be no. Okay. Here's what I'm going to do. I'm going to say, let's first create a bunch of vertices for my variables. So I create one vertex for each variable. Let's call it X. And let's say that I also create a vertex for the negation of each variable. Okay. For each variable and one for its negation. Okay. So on this particular example, I will have in my graph X, Y, and Z. And I'm going to also have, oh, I have W there as well. Okay, so W, X, Y, Z. But I'm also going to have vertices for their negations. Not W, not X, not Y, and not Z. And I'm going to connect these pairs of vertices. So connect them by an edge. So in my graph, I'm going to have this edge, this one, and this one. Now, what is the intuition? What do I want to do? I want to say this is an input to an independent set problem. So whatever vertices I take into my independent set are going to be the variables that I set to true. Okay. So I cannot set both W and negation of W to true. That's why I add an edge between them so that no independent set can contain both W and its negation. And I'm doing the same thing for all of my variables. Okay, but at this point, I have kind of a nonsensical graph because, I mean, you can easily compute the largest independent set here. You can just take one vertex from each pair, right? I have to continue, and I have to make sure that my graph really represents my original three set inputs. Okay. Now, I'm going to create some vertices for clauses. So I say for every literal in every clause, I'm also going to create a vertex, and I'm going to create a triangle between the vertices in that literal, in that clause, sorry. So I say for every clause CI, which is of the form Li1 or Li2 or Li3, just create a triangle with these three vertices. And I'm introducing new vertices now. Okay, so create a new triangle, Li1, Li2, Li3. Okay, let's go to our example. This is the graph that I already had. So I have X or Y or not Z. I'm going to create a triangle, X, Y, not Z. And I'm going to connect all of them together. Okay. Now I'm going to create another one for this one. And that's not X, W, Z. And I'm going to connect them. Okay. So what is the idea? The idea is that from every triangle, I want to take exactly one vertex. And that's going to tell me which literal in the current clause is satisfied. Okay. So for example, if I satisfy X, I want to take X from here. If I satisfy Z, I want to take Z from here. But from every clause, I want to take only one of the literals that satisfies it. Even if I have several literals, I want to make sure that I don't take more than one from each clause. So that's why I'm creating a triangle to make sure that from the construction or the gadget for each clause, I'm taking at most one vertex. Okay. But right now, my variables and my clauses are completely independent of each other. That's not how three-set works, right? I have to somehow make sure that they actually correspond to each other. So here's the idea. Let's say that from this clause, I want to pick X. So I want X to be in my independent set. What does this mean? This means that everywhere else, in every other clause, X is also satisfied, right? But I have to somehow enforce this. How can I enforce this? Well, I know that if I take X into my independent set, I'm intuitively thinking that I want to set X to true. But that means that I cannot set negation of X to true. So I cannot have this vertex in my class. And that's the whole idea. So I'm going to take this X here and connect it to the negation here. I'm going to take the Y and connect it to its negation here. I'm going to take negation of Z and connect it to Z, because negation of Z is Z. And the same thing here. So negation of X will be connected to X, W will be connected to not W, and Z will be connected to not Z. Okay, this is my graph. Okay, so this is the last part. So I say connect every vertex Lij to the variable vertex of its negation. And that's my reduction. So that's how I convert a 3-set instance to a graph, and I pass this graph later to the independent set. Okay. Now, up until here, I was just telling you the intuition. I was telling you why I'm doing these things. But now I have to actually prove that my reduction is correct, right? So what are the things that I need to prove? I need to prove that this reduction works in polynomial time. And I need to prove that the independent set problem returns yes on this instance if and only if the 3-set problem returns yes on this. Okay. Oh, and I forgot one thing. In the independent set problem, we have to also give a value of k. Okay, so here's the thing. I ideally, intuitively, want to take one vertex from each one of the clauses and one vertex from each pair of variables and negations here, right? So I want to find an independent set whose size is the number of variables plus the number of clauses. That's the number that I'm going to use as my k. So I have to write that as part of my reduction too. So k is going to be the number of variables plus the number of clauses. And I'm asking if there is an independent set of size k. Okay, now that we have the reduction, why does this run in polynomial time? Well, you can just go and analyze the algorithm. I'm creating one vertex for every variable. So if I have n variables, this is On. This part is also On. Then I'm adding On edges. And then here you can see that for every clause, I'm also doing a constant amount of work. I'm just adding 3 vertices, a triangle between them, and one edge from each of them to somewhere before, right? So this is actually definitely polynomial time. It's even linear time. So the next thing is that I have to say it preserves the answer. So if the answer for the original 3-set instance or input is yes, then the answer for the independent set should be yes as well. And if it's no, it should be no here as well. So suppose that the original 3-set instance is satisfiable. So the answer is yes. What does that mean? That means that I have an assignment to these variables such that this 3-set will be satisfied. Now I come here, and on this left side of my graph, I take all the variables that were set to true. I take those vertices into my independent sets. And then for every clause, I just find one of the variables in that clause that is set to true, and there is at least one variable because the clause is satisfied, and I add that to my independent set as well. This gives me an independent set of size k, which was the number of variables plus the number of clauses. And so if the original 3-set instance is satisfiable, then the independent set input is also going to be a valid yes instance of independent set. Okay, now let's say that the original 3-set instance is not satisfiable. Okay, so I don't have any assignment that would satisfy all of these constraints. If that's the case, I want to also prove that I cannot possibly have an independent set of size k here. Okay. Now I prove this by contradiction. suppose that I have an independent set of size k. If I have an independent set of size k, from every triangle, it can take at most one vertex, because all the vertices in triangles are connected to each other. And from every pair here, it can also take at most one vertex because they're connected to each other. So overall, the number of vertices that I can take into my independent set is at most k. I can take one vertex from each pair and one vertex from each one of the triangles. So if I happen to have an independent set of size k, it means that that's exactly what it did. It took one vertex from every pair here and one vertex from every triangle here. Okay, but now I claim that the vertices that it took would also give me an assignment to variables that would satisfy the original 3-set instance. Okay, the vertices that it took are an independent set. So it never takes a vertex x and also its negation. So from every vertex and its negation, it's taking only one of them. So I have a valid assignment. That's the first point. Now I want to say that this assignment satisfies my 3-set formula. I say that let's look at each clause of the 3-set formula separately. That clause corresponds to a triangle. But from that triangle, I took a vertex. And let's say, for example, if I took x here, it then means that because this x is connected to this negation of x, I didn't take negation of x, which means I took x here. So basically, it means that the clause is satisfied. So because of this, the reduction is over and it's correct. So my graph here will have an independent set of size k if and only if the answer to my 3-set instance is yes. Okay. Now, again, since this was a polynomial time reduction, it means that if someone magically gives you an algorithm or a black box that solves independent set in polynomial time, then you can also solve 3-set in polynomial time. Because you just apply this transformation, now you have an independent set instance, you apply the black box algorithm. Nice. Okay, so let's look at some other problems now. I want to look at the problem of vertex cover next. So this is vertex cover. My input is again going to be a graph G. And some number k. And the question that I want to answer, so my output should be yes if the answer to this question is yes. The question is, does G have a vertex cover of size k? Now, what is a vertex cover? A vertex cover is a set of vertices that covers all of the edges. So can I choose k vertices such that I am sure that I have chosen one endpoint of every edge? Okay. So the other way of asking this is that, are there k vertices? Or let me give it a name. Is there a set, let's say C, subset of V, such that there are k vertices in C and every edge has one of its endpoints in C, maybe both, but at least one. And every edge has at least one endpoint in C. Okay, this is the vertex cover problem. Now, usually, if we wanted to look at this as an optimization problem, we want to minimize the size of our vertex cover. We want to pick as few vertices as possible to cover all the edges, right? But again, I'm looking at it not as an optimization problem, but as a decision problem. So my input is already giving me this number k, and it's asking me, is there a vertex cover that has size exactly k? Okay. Now, I want to prove that this problem is also NP-complete. As usual, I have to prove it's in NP. I don't have time for that. Believe me, it's in NP. Okay. Then I have to find a reduction. Now, I already know 3 NP hard problems. I can pick any of these and reduce it to vertex cover. It would actually be a nice exercise for you to try to reduce 3-sat to vertex cover. But it's easier, at least for me, to take independent set and reduce it to vertex cover. I get to choose which NP complete problem I want to reduce. I reduce from independent set to vertex cover. Okay. Now, why is that? Because I want to prove a very simple lemma. This is my lemma. I say that in a graph G, let's call it VE, if I is an independent set, then the complement of I, all the vertices that are not in I, is going to be a vertex cover. Is a vertex cover. And also the opposite. If you have a vertex cover, its complement is going to be an independent set. Why? It's just following the definition. What does it mean for a set to be an independent set? If I have my set I, let's say this is my set I, it has a bunch of vertices in it. It's an independent set. So no edge has both of its endpoints in I. So any edge that I look at is, and this is V minus I, any edge either has both of its endpoints in V minus I or one of its endpoints in V minus I. Right? So V minus I is a vertex cover. Now, this argument works in the opposite direction as well. If you have a set that is a vertex cover, its complement is going to be an independent set. So, if I ask you, does this graph have a vertex cover of size k? That's the same as asking, does it have an independent set of size n minus k? Right? Because if the graph has a vertex set of size k, I just take all the other vertices, they're going to give me an independent set of size n minus k. And again, this argument works in the other direction, it's reversible. So this is my reduction. I say that if I want to solve vertex cover on a graph G and with parameter k, I would just say that this instance is equivalent to independent set on the same graph, and the parameter just becomes n minus k, where n is the number of vertices. So again, super easy reduction. Now this means that if I have an algorithm that solves vertex cover in polynomial time, I also have an algorithm that solves independent set in polynomial time. And by the way, this was a two-sided reduction. So I didn't just reduce vertex cover, sorry, independent set to vertex cover, I also reduced vertex cover to independent set. So if I have an algorithm for any of them, I have an algorithm for both of them. Okay, so this is our current situation. I reduced independent set to vertex cover, and because my reduction was reversible, I have also reduced vertex cover to independent sets. Okay, let's do another problem, and this is the problem of clique. So the input, again, as usual, is a graph and some number k. And the question that I want to answer or decide is, does this graph have a clique of size k? Are there k vertices such that every pair of them are connected to each other? Okay, so are there k vertices? Let's call them, it's a clique, so I'm again going to say C, subset of V, such that for every two vertices U and V that are in C, I know that there is an edge, UV is in E. Of course, I want to say for every two vertices that are not equal to each other. Sorry for the bad notation. Okay, so whenever I take two vertices out of this set, I want to make sure that there is an edge between them. So for example, a triangle is a clique of size 3, right? So basically I'm asking, if my K was 3, I would ask, does my graph have a triangle? If my K was 4, I would ask, does my graph have this as a subgraph? So 4 vertices that are pairwise connected to each other. Okay. Now, again, I want to find a reduction from one of the problems that I already know are NP-complete to this problem, to the problem of clique. You have to prove that clique is in NP. Do it on your own. Okay. So, which problem should I take? I take independent set again, because here's the idea. Suppose that I take a graph and I complement my graph. So I take a graph, and for every pair of vertices, if there is an edge between them, I delete the edge. If there is no edge between them, I add the edge. Okay, I call this the complement graph. Now, an independent set in the original graph is a clique in the complement graph, and vice versa. Again, you can prove this. So it's a very simple lemma, just like the previous case. Let's say, let me show the complement graph by G bar. So G bar is the complement of G, which means that an edge exists in G bar if and only if it doesn't exist in G. Okay, but it has the same set of vertices. Now the lemma is this. The lemma is that I have an independent set in G of size K if and only if I have a clique in G bar of the same size K. Okay. Now I'm not going to go through the details of this proof, it's pretty easy. Okay. So again, this is a two-sided reduction. So if I have an algorithm for independent set, a polynomial time algorithm for independent set, I can apply this and get a polynomial time algorithm for clique. If I have a polynomial time algorithm for clique, I can apply it in the opposite direction and get a polynomial time algorithm for independent set. So clique and independent set are equivalent problems in this sense. So I have the problem of clique now, and I just showed you a reduction from independent set to clique and a reduction from clique to independent set. Okay. But of course, all of these problems are in NP. And so now all of them are NP complete. But if a problem is NP complete, I said that means you can reduce any problem in NP to this problem. So I should be able to basically take any two of these problems and reduce them to each other. Now, in some cases, I have shown you some of the reductions, but let me actually do a reduction that creates a cycle in this graph because I like cycles. So let's say I want to reduce clique to CNF set. Okay. So I want to do this. And basically, this is further evidence that all of these problems have the same difficulty, in the sense that if you have a polynomial time algorithm for one of them, you have a polynomial time algorithm for all of them. Okay. Let's do this. Clique to CNF sat reduction. So I'm given an input of clique, and I want to turn it into an equivalent input of CNF sat. I want to write a satisfiability formula. So my clique input is going to be a graph G and some number K. Right? And the question is, does G have a clique of size K? Let me again do an example. Let's say this is my graph G. So I'm going to label my vertices. And just to make things easy, let's say that my K is 3. So I'm asking, does this graph have a triangle? Now, of course, as a human, you can just look at it and say yes. But of course, we care about the much bigger instances of this. Okay. So now I want to turn this input into a formula in SAT. What do I do? Well, first, I'm going to define a variable for each one of my vertices. And that variable, again, intuitively, is going to tell me whether that vertex is in my clique or not. Okay, so my first step is define a variable xi for every vertex I. So my variables here would be x1, x2 to x5. Okay. Now, I have to write some constraints. What are my constraints? My constraints are going to say that if I have two of these variables that are set to true, then I must definitely have an edge between them in my graph, right? But I want to write this just as a formula without talking about the graph. Okay. So I'm going to make this a little bit easy because all I care about here is to do it in polynomial time. So the reduction I'm going to give you is not optimal at all. I just care that it runs in polynomial time. I can waste as much time as I want as long as I don't use more than polynomial. So I'm going to say define a variable for every edge as well. I don't need this. Honestly, you can just do it with variables for vertices, but who cares? The number of edges is polynomial anyway. I have at most n squared edges. Okay, so define a variable, let's call it yij for every edge ij. And this is for i's that are less than j. So I'm putting an order on it. So for example, I will have y12, y14, and so on. But instead of saying for every edge, I can actually do it for every pair of vertices. So for every pair ij of vertices, define a variable. And then I want to add a constraint that this variable is 1 if there is an edge in the graph, and this variable is 0 if there is no edge in the graph. Okay, so here's the thing. I say for every edge ij, add this clause to the CNF SAT formula. What is my clause? My clause is very simple. It's just yij. Remember, in CNF SAT, I can have clauses with any number of literals. I'm just adding a clause with one literal. I'm saying that yij should be true when the edge exists. And also for every non-edge, so for every pair ij such that there is no edge from ij, add this clause. My clause is just going to be not yij. Oh. So what do I have right now? I have a bunch of variables. I have one variable for every vertex, and I have one variable for every pair of vertices. Now, intuitively, I wanted to say that if a vertex variable is set to true, that means I want to take it into my clique. If an edge variable is set to true, it means that that edge actually exists in my graph. Okay. But I want to also write the constraint that whatever I'm taking into my clique is actually a clique. So I want to write the constraint that if I have two variables that are true, so if let's say I've set x1 and x2 both to true, it means that I've taken vertices 1 and 2 into my solution. So I want to make sure that there is an edge between them. Okay. So this is the last part of my reduction. I say for every two vertices, let's say I and j, I want to ensure this. I want to ensure that if I have xi and I also have xj, then I have yij. But this is not a CNF formula. I have to translate it. I have to write an equivalent formula that is in CNF form. Okay, help me with this. How would you translate this to CNF? So this is equivalent to saying yij or not xi and xj, right? Which is the same as saying yij or not xi or not xj. Okay, and this is a CNF formula. So I add this clause, add the clause, this thing, yeah. And now it's pretty easy to check this. Again, if you're writing this in an exam, you have to write all of these things carefully, but you can check that my formula will be satisfied if and only if there is, if and only if what I'm assigning here to my variables is a clique. But there is still another part remaining. My question was not just whether I have a clique or not. My question was whether I have a clique of size k. Okay. How can I put that part into this? How can I say that my clique should have the size k exactly? So this is the last part, part 4. I want to write constraints. So add constraints that ensure this, that ensure x1 plus x2 so on to xn is k. Because this is the number of vertices that I'm taking into my clique. But again, this is not CNF. You don't have sum in CNF. How can you do this? How can you have addition? Now, how many of you have passed computer architecture? So using and or and logical gates, you can do addition, right? I'm not going to give you the details of that, it's painful. But if you've passed computer architecture, you know that you can translate this to a combination of logical gates, a logical circuit. And that logical circuit is a CNF formula. So basically, I'm saying add CNF constraints that ensure this. And again, just trust me that it's doable. Okay, we don't have time to do it. But the important point is that now I got a reduction, assuming that I can do this part. And my reduction runs in polynomial time. And other than running in polynomial time, it also preserves yes instances and no instances. So if I give you an instance of clique, you can apply this reduction, you will get an instance of CNF SAT. And then if you have a SAT solver, which is actually a real thing, by the way, there are a lot of tools that are just created with a lot of really good heuristics for solving SAT instances. Then you can give this problem to the SAT solver, and hopefully the SAT solver solves it for you. And if the SAT solver works in polynomial time, and we don't know if such a SAT solver exists or not, then this algorithm for clique would also be polynomial time. Okay, so we have all of these reductions. Should I do more? We have 5 minutes. Okay. Let's do one more reduction. Let me do it from 3SAT. I'm going to tell you how the reduction works. I'm not going to prove it to you because we don't have time for it. I want to reduce it to subset sum. Okay. So what is subset sum? This is the subset sum problem. My input is just an array of integers, an array, let's call it A of n integers, or of, let's call it m integers. And these integers can be positive or negative, or 0. And I also give you some number k, and this is also an integer. It can be negative or 0. And the question I'm asking you is that can you choose a subset of the integers given in the input such that they sum up to k? Okay, so is there some subset, let's say S subset of A, such that the sum of all the values in S is equal to k? So for example, maybe I tell you that my A is 2, 5, minus 1, 4, 0, 7. And then my K is, let's say 14. Can you get a sum of 14? Yes, I can just choose 2, 5, and 7. Can you get a sum of 13? Yes, I can choose 2, 5, 7, and minus 1. Okay. Can you get a sum of minus 2? No. So this is basically the question. And I'm claiming that this problem is also NP complete. Again, it's in NP because if an answer exists, I can give you the answer and you can verify in polynomial time that it's the correct answer. Okay, so it's in NP. But how do we find a reduction from 3 sets? Okay, I cannot find that thing. Okay, so let's say I have a 3-set input. And let's say my 3-set input is something like this. X or Y or not Z, and not X or not Y or Z. Okay. I want to translate this to this. And it's very weird because it seems like they have nothing in common. Right? But the trick is in how I create my integers. So here's the thing. I'm going to create really long integers. Because remember, all I have to make sure here is that the size of my input increases by at most some polynomial factor. I'm not saying that these are 32-bit integers. I'm just saying they're integers. So as long as I can represent my input in some finite polynomially bounded lengths, I'm happy. So I'm going to create huge integers here. Now, here's what I'm going to do. I'm going to look at these integers in binary, and I'm going to say the binary representation is going to have many digits. Let's say my binary representation is going to have 5 digits for every variable and 5 digits for every class. So again, let's say that I have, I don't know, V variables and C clauses. Okay. I'm going to create numbers that have 5 times V plus C bits. So every one of my numbers is going to have 5 bits for every variable and 5 bits for every class. Okay. These are huge numbers. Now, what am I going to do? I'm going to create one number for each variable. For each variable X. Now, how does my number look like? Look, I have 5 digits for X. By the way, I chose 5 randomly, probably 2 would have worked. And I have 5 digits for Y. I have 5 digits for Z. And then let's call this one clause 1 and this one clause 2. I have 5 digits for clause 1 and I have 5 digits for clause 2. So let's say that I want to create a number for variable X. What I do is that I fill out the part for X with 1. So this means that this is the variable X. Okay. And then I put zeros for every other part. Am I putting 4? Yeah, 4, whatever. Okay. And I put zeros here for Z as well. And then if setting this variable to 1 would satisfy C1, I put a 1 for C1. Otherwise, I put a 0. So it does satisfy C1, so I put 1 here. Does it satisfy C2 if I set X to true? No, so I put 0 here. This is what I do for X. So this is the number corresponding to X. And I do the same thing for negations as well. So for not X, I create a number. Again, it uses the variable X. So I'm going to have 1 here. It doesn't use Y, so I'm putting zeros there. It doesn't use Z, I'm putting zeros there. If I set not X to true, would it satisfy C1? No. So I put zeros here. Would it satisfy C2? Yes. So I put a 1 here. Okay, so this is how I'm creating my numbers in binary. I create one number for each one of my variables and for each negation of a variable. And I add all of these numbers to my set. Now, what do I want? I want a bunch of numbers such that when I add them together, they correspond to an assignment that satisfies every clause. So I want to add the numbers together, and then I want to have a 1 in every one of these clause parts. Okay, so what is the sum that I'm looking for? Like, what is my desired K? What do I want to be the sum of all my numbers? Well, I want to say that I have a 1 here, which is equivalent to saying that I either took X or not X, because they both had a 1 here. If I take both of them, then I wouldn't have this representation. I want to have a 1 for Y, which is, again, equivalent to saying that I should either take Y or not Y. I want to have a 1 for Z. I want to have a 1 for C1, which means that I want C1 to be satisfied, and I want to have a 1 for C2. So this is the desired sum that I want to get. Now, this reduction is still not complete. Because imagine that I can somehow satisfy a particular clause in 2 different ways. Then the value for that clause will be added twice. Okay, so my sum would not be this, it would actually have a 2 for that particular clause. So for every clause that is satisfied, I can have a value of 1 or 2 or 3 in the binary representation. But I have to fix 1 case, so I want to make sure that I have a value of exactly 1 for every clause. So now for every clause, I'm going to add integers that can subtract that clause. Okay, so I say, let's take this. For every clause Ci, for example, for clause C1, I'm going to add this integer. First of all, it's a negative integer. And then it doesn't touch the parts that correspond to variables. It has 1 for C1. It doesn't have anything for C2. And I add this to my set twice. Okay, so add this twice to N, to A, or have 2 copies of it. And similarly, for my other clause C2, I will have this number, where it's a 0 here, and it's a 1 here. And I add this one twice to A as well. And then I ask, is there a way to get a sum of some subset of numbers in A such that the sum is this desired value K in binary? And now you can see that in order to get that, I should have a 1 for each one of my variables. So it means that I have to take either that variable's number or the number of its negation. But then this might satisfy some clauses. I have to satisfy each clause at least once, right? But if it doesn't satisfy a particular clause, it will never give me this. If it satisfies a clause in more than one way, it will give me, let's say, a 2 or a 3 here. But then I have 2 copies of this negative number that can be added to cancel out the extra things that I added for this clause, so that I can get the same sum. So this is a valid reduction. And again, I said, use 4 bits for each one. It's up to you. Use as many bits as you like. Just make sure that you don't have a case where the numbers sum up with each other and then you carry them and they interfere. So who cares? Just use n bits for each one, as long as it's polynomial. Okay, so you can verify that this runs in polynomial time, and then you have the answer to your subset sum instance is yes, if and only if the answer to the original 3-set instance is yes. Okay, so going back to our picture, where is our picture? These are the reductions that we have seen. Now, here's the weird one. In the next session, we're going to see a reduction from subset sum to knapsack. So knapsack is also NP-complete. But I want you to think about it until tomorrow, because if you go back to our algorithms for knapsack in the dynamic programming sessions, it feels like we had a polynomial time algorithm. But actually, tomorrow we're going to see that knapsack is NP-complete.